Hello and welcome back to my show. Today we're doing an episode with Leaf, and I would like to program another algorithm today, and not so much an algorithm as a container. This will be a vector container. For those of you that don't know me, my name is edA-qa and I'm a creator of the Leaf language, and I also work at a company called Fuse where we do cross-platform products. But today I will be focusing on Leaf. Language is still in development, lots of stuff to do, but it should be good enough for us to write a vector. Last time I wrote a linked list and it worked okay. There was a few to-dos and I've since fixed them. The to-dos were minor syntax errors and compiler errors. And as we encounter them this week, I'll fix them as well. Now I'd like to try and see what we get today. So quickly adjust my screen so my browser isn't overlapping. Should be okay. And we'll start with a container. We're going to start with I'll increase the font size here so you can see it a bit better. It's getting really wide, unfortunately. I'll create a new directory. These are all put on my GitHub account then, and we'll say vector. I'll be sure to push it at the end of the show. And we'll just use the one window for editing, and I'll make it a bit bigger. And this is the basic Leaf program. And we're going to import standard.print hello. Just to show you how it works again if you've not been used to this. And it's also just going to make sure all my tools are actually correct. And we'll call it main.leaf. That should give us a syntax highlighting, and we should be able to see what happens here. And you know what I forgot to do? I forgot to open up the chat window. Alright, let me just quickly do that. And see myself for a second, open up chat, and just make sure that's on my screen. See myself for a second, open up chat. Wonderful. Okay, and of course it's always the wrong size, that's not a problem. Oh, it really doesn't like being the wrong size. Alright, sorry, I should have had this set up before. I usually do. Should be okay. Just so I can see something, we'll put it there. If there's somebody watching, you can chat. Just ask me questions along the way. I'm doing this mainly to answer questions about algorithms and to show off Leaf a little bit. Okay, so that's back to main.leaf. I've got the main program, and if I go back to the command line, I should be able to run it in this directory. It says hello, and putting a line feed should be good. I don't remember if I added a print line. Let's find out. I thought I might have. And I did, but it requires the tuple, so that should be fine. Good. And that prints out a line. And I'll make this a bit smaller in the chat as well. I don't know why these windows get stuck. This is weird. Now I like the sticky windows, but sometimes they get in the way. Okay, that should be enough to see it. So we say hello. And we'd like to make a vector. To recap, a vector is a data structure where we have items in sequence, and you can access them by a subscript, or rather say random access to set and get these values. And I think I had a drawing program where I can show this on screen. Oh, I don't remember what it's called. Whatever, I won't use it today then. A nice little program to draw on the screen. I'll just explain it. So you're familiar with arrays from normal programs. So let's just create a quick array to see what we're up with. So we have an array. Sorry, this is the old syntax. It's now type array and say integer. And arrays are a fixed length, so we have integer 5, and then we can say q0 equals 1, q2 equals 3, and then we can print them out, for example. I'll even print q1 because it'll show it's initialized to 0, q2. Okay, that prints out 103, much as we'd expect. Now the idea of a dynamic vector is that we want to be able to push and pop elements off of a vector as we're writing it. And this will create little blocks of structure. And so it has to adapt in size. So let's start with the basic. We have to create a class. And we're going to call it vector. And it's going to be a parametric class, which is important. And the basic part is data. Where is the data actually stored? And this is going to be of T array. It's an array of T, and we don't know the size of it yet, and that's the whole point. So we're going to have to keep the size as well. We'll keep an integer size. And we'll make a constructor, a default constructor. Struct. And we'll say size equals 8 by default. Actually, sorry, this is not size. This is going to be capacity. And we have a separate one called size because we don't know. These are two different values. The capacity is how much array space we actually have, and the size is how much is being stored in it right now. So if you set the size to 0 and our capacity equals 8, and let's actually allocate the array now. Type, oops, array of type T, and I've inherited this T standard from C++. I'm not entirely sure why, but I just kind of like it. And we have a capacity. These are all default initialized, but since we only have size of 0, there's nothing actually in them yet. So let's remove this stuff here. Let's create a var q. I just like q, and we don't have to use. We can use a simpler syntax vector. Let's store integers in this again. Integers. Now we can't really print anything out here yet, and so let's do an add function or add. And this has to take a value of T. And for the moment, let's just assume that we have enough space in the vector, and we'll show the basic operation. So that's going to be data size, because this is the next one available, equals x, and then we do size plus equals 1. Okay. Now I've marked these with underscore because Leaf, we don't have the private or protected access yet, so I'm just using the standards come from Python, the convention that if it's underscore, look, this is supposed to be private. And it's good to work with now. Eventually I will add private features so that you can actually enforce these rules and we don't need the underscores. But for now it should be okay. And so let's do the next step here. I'm going to say size. We can make a function now, but let's call it GetSize because I don't have getters. Let's just do a GetSize. And this is return size, very simple. And let's do a simple get where we have an index. Say index at integer. And again, we won't do any bounds checking here. Let's just do return data. We can add bounds checking later. So this should be enough for us to add a few values. Add 5, q.add 9, standard.println. We're going to expect the length to be 2 now, so we'll say q.getSize. That'll be 2. And let's print out the 2 values that we have. q.get, sorry, 0. It's cold in here today. I'm having a hard time typing. I sometimes type semicolon. You can use it or not. I prefer not using them in Leaf, and the whole language is designed around not needing the semicolon. Okay, invalid input node. So I'm still stuck in these bad error messages. I think it's the next one I'm going to get to. We just kind of have to define what the issues are. Okay, and that was the wrong type there. Redundant spec line 414. What did I say? Oh yeah, sorry. This is bad of me. It's an array of T. I don't have that as a syntax. Sometimes these syntaxes from the language leak in. This is very clearly an array of T. And we have a problem at 11.9. Type. This is supposed to be type array T capacity. Pooh. Well, I'm not sure what actually went wrong there. I had to think about this one for a second. Because this is not array, this is array T. Sorry. Alright. So now we have what we want. We have 2 and 59. This is the 2 values right here. and we added 5 and we added 9 and we have the size. This is much what we expected, and so we have the very basic vector working. And I say basic because it only goes up to capacity 8. If you add more than 8, bad things will happen. I don't do a lot of bounce checking yet, but once this is fixed in the leaf, if you add beyond 8, it's going to give you an error and say, look, you can't do this, it's beyond the errors. It's supposed to be safe language, but hey, some things aren't quite finished right now, so we'll deal with that. Now, before we get to the dynamic part, what I'd like to add is a way to iterate over this array. And when we did linked list, we created a ForEach function. And we created ForEach. And we said, what type of function is ForEach? Well, we said it's a function that takes an item of type T and returns nothing. And this is part of the high-level function approach. And what we're going to do for all of this is loop over it. And we have a for loop for this, except I don't know if I have the range here. So let's do it the horrible way first. We're going to say var I. We're going to say while I is less than size. This is a very clear approach. We're going to do f data-I to get each element in the loop. And we're going to call the function on it. So this says as long as we have data, forget to go to the next element. Go to the next element. As long as we have items in here, we'll call the function with that item. So instead of the standard print line, we should now be doing q.forEach and give it a function standard.print x. I'm going to print x with a space as well. We don't have a print line here because we want to put one print line at the end, and that'll finish it off. And parser stuck doing nothing. Oh, I love such errors. 48. Let's see where we're at. Stuck doing nothing. And it's a parser error, which is very curious, which means I had some weird parsing error. Okay, it's right here. I'll have to check that. I'm going to put a little to-do here. Missing end parent. Got stuck in parsing error. And I fix these later. I go back and I fix them, I remove them, and then I see what the problem is. And so now we have 5 and 9. So we can see that we actually loop through it. And if we added another one, 5, 9, and 1, 3, 5, 9, and 1. So that's good. And so let's change the print statement here. Let's show the whole size of it. We're going to say size. That's what equals comma q.getSize, and then we'll put a space and list the items in the array. So we can show it all at once then right away. This is just mainly debugging. We want to see what happens. But this is enough for us to now to see that there'll be to show the output. So if we do, we'll see the output and we can debug it as we add the dynamic aspects to it. Okay, now what do we have to do next? We have to worry about this capacity 8. So I added 3 items. So what happens if I put a 2 here? This is going to be bad. Okay, this worked, and this is really bothersome, okay? And I'll explain first of all why this works. The mainly reason this works is even though I put a capacity of 2 and we've added 3 items, is because I don't have the bounce checking yet in Leaf, and because this program is extremely simple, we were capable to just overwriting the end of the memory and nothing happened. It just happily did that. This will clearly not work. This will produce an error. And this get function should also produce an error. And for example, we might want to check index is less than 0 or index is greater than or equal to size, then fail with string tag invalid index. Okay, and I have an error there as well. Okay, let me figure that one out. But this is what it would look like. And failing to instantiate template. This is part of the reason why I do these streams, so I can find these little things, because a lot of this stuff, I have lots of test cases, but some of this stuff just doesn't come up. The fail statement. What unsupported pre-clone means is that basically it just doesn't work inside a template yet, or a parametric. And it must be a weird corner case because I tested this, but there are a few corner cases, and they still come up quite frequently. But we're going to have to ignore the error handling for now and worry about this capacity thing. So we have capacity 2. So what happens is we want to check the capacity and add. So what happens if we say if the size is greater than capacity, actually greater than or equal to, then we have to expand. But I don't have an if statement, just remember that. You can actually do an if, but it's differently. So I usually use the then statement instead. And then covers this. This is the syntax. So if our size is greater than the capacity, then we're going to expand. And let's write an expand function down here. Let's write it before the ForEach define. Actually, before all accessors. And what does expand do? Well, with expand, we want to give more space. So we have to increase the capacity. So the first thing we want to do is we want to say new capacity equals capacity, and we're going to multiply by 2. And 2 is not just some random number. This has to do with the complexity of this, and I'll get back to this later, but this actually guarantees a certain type of constant time complexity, amortized time. If you do anything less than 2, you don't get that, but I'll come back to that later. And so now we need new data, and we have to do type array-t with the new capacity. And this creates a new array, but now we actually have to copy the data over. So say for I equals 0, well, I is less than, not the new capacity, but the size. We're going to do new data, I equals the current data I. Just copy it over, straightforward copying. Now we just have to get rid of the old, we have to do cleanup. So the new capacity equals new capacity, and the new data equals new data. This there's a bit of an error here, and I'll get back to this later too, is that these arrays are currently by value. And by value, that means is when I do an assignment like this, this is copying everything by value. And once this is working, I'll show you how we should fix that. Okay, but this should be expanded. We've doubled the size, so we do 3 adds, and this should actually expand now. Except, yeah, it's very good when making a loop to increment the counter. And I'll also check, in my tests I have a standard for loop. Let me check quickly if I actually have this in the standard library. We have a package, no, where is that? I forgot where I put my standard library. There it is, standard library, standard, and we do have range. Oh, it only increases the size file. So your range to begin to end, that's what I wanted. Okay. Let's check it works. Okay, it's adding it, which is good, which means it's called this. And so we also have for I in standard range 0, size, and that should do the same thing with less effort. Okay. We'll clean up the other loop as well. The reason I had to check is because I don't know if I had standard range available last time, but now I do. And standard range is your standard loop, and it's a lot cleaner than doing incrementing on your own. Okay. So this is the basic expanding. So we can add all sorts of values here if we wanted, and we could even do another loop down here for I in standard range. And let's just add a whole bunch of numbers from, let's say, 5 to 15. New q.add I times 10. This will probably invoke expand a couple of times. Okay, that was interesting. I couldn't open the file. I've had this problem in the file system too with my build system as well. If you modify it too fast, it can't open a file, and this is really strange. This might have been Kate saving it. Okay, so we have the big list of numbers, and if you want to see that expand's actually been called, we can put a printout here in it as well. Expand capacity from, and let's put the current size, current capacity. and this takes a tuple again. I don't have the var args working yet. I'm not sure if it will. So we expanded the capacity 3 times, which is good. We still call it the function. Now, this should be enough to. This is our basic vector. This vector can do, well, addition. That's all we needed to do. We can add things to it. We can't remove things. We have a get function which returns by access. Get isn't ideal yet. So, example, if you wanted to get the value of q.get 0, this is not the syntax we want. What we actually want to do is the native syntax of #0, which is index 0. But again, this is one of those areas in Leaf that I don't have the overload for that working. The idea is that I'd have an overload function instead of get. I'd have something called subscript, and I'd overload it. So I'm going to put this as a to-do because this shouldn't actually be very hard to get working. These aren't the types I can do in the show. Okay, now I'm going to make one more change first. Let's say data is a shared array. This is important, and so this is a shared array and shared array. That should be all that changes. Okay. The biggest difference between an array and a shared array is that arrays, as I said, are by value, and this has become very strict in Leaf that everything is by value. It doesn't matter what type it is. By default, it's always by value, and that means when you copy it, it does the deep sort of copy. All the items are copied through it, and this even includes class, like vector itself. You can actually do a copy of it. The copying is probably not defined here yet. They're doing kind of shallow copies. I'll prevent it. And this is to provide consistency and also to do extended types. Because when you do, say for example, Java and you have a class, it's always by reference, which makes it very hard to create value types. And it creates an inconsistency in the syntax. But it's something to get used to because we have that I have to remember to type shared array on this. And we'll see how that works. There is another type of class called a service, and the difference between a service and a class is that the service class is always shared. It has a few other minor changes, but that's about it. Okay, so we have add. Let's move add on and exchange and expand. Now I want to show one thing first, is that I always like going over the complexity of these things, and use the theta notation for this. What is theta? Oops. Now unfortunately I still can't get my dead Greek keyboard working, so I have to copy and paste the theta, and I don't like typing big O notation. I actually like big theta notation because it's actually more correct. And so we have to decide for add here, what is the complexity of this? What is the time complexity of add? And so we take it, let's ignore capacity, the expand for a moment. If we just add an element, this part here becomes a theta of 1. We've done a constant time algorithm. Now the question is, what is expand? What is expand? And this is where it starts getting interesting, because the time complexity of expand, well, it has to be n, because we've doubled the size and we've had to go through the entire list of values. And that's an n operation. We have a loop in there, it's n. Now, this is how C++ arrays typically done. In a lot of languages we do it that way, but these are always quoted as being constant time. And this is very interesting, and it's kind of an abuse of the language, is that this isn't constant time, but it's very close. And it's something called amortized constant time. So this is 1 in amortized constant time. What this means is because we double the size of this array, each time we double it, we can actually show that overall, the average of all the calls, all the times I call add, is going to work out to be about constant time, because we very rarely call expand. And because we could do it by 2, we're very specifically increasing the amount to make it amortized constant time. Now, amortized constant time just basically means in the long run, if I keep calling add, it's going to effectively be constant time, and it's going to behave that way. Occasionally we have this horrible order n, but generally it's amortized. And I'll show you the link, and I'll copy it to the chat. If you're interested in more information on this, I wrote an article about amortized constant time that goes into a lot more detail and can get into more details. And in particular for vector right here, and you'll see the actual title there is the amortized constant time of vector insert is 3. I put the link in chat. And I'll get into why it says 3 here, and notice this is not big theta, this is just 3. And 3 obviously reduces down to a theta of 1, because we only care about the order. And so I'll let you look at that on your own. If you go through that, those are some details about how that actually becomes constant time. Okay. Now the next thing for a vector is we'd like to actually remove stuff. But one note about why a vector needs to store this in an array. We have something called the get function. Now most languages, when they have a vector type, they make a guarantee. They say the time is, whoops, I gotta copy my little symbol again. They give an absolute guarantee for the time of 1. This very much constrains how you can store the vector. If you want to have a constant time, it means this operation has to work. You have to be able to take a data index and give it index. You can't have, say, a linked list because that involves an iteration. You can't have blocks that store. You can't have any type of data structure other than just this one thing where an immediate jump to that array index gives you the value. Now this is a fairly tight constraint on these operations, and this constraint isn't even, say, amortized. This is a strict constraint. This is so not amortized. This is strict. I find it unfortunate that a lot of standards don't necessarily make that statement, the difference between amortized and not amortized time. Because if I allow an amortized time for get, that I can actually use different algorithms. But it gets a lot tricky because if I call get 1,000 times in a row, it's hard to amortize. So when you have this and it's not amortized strictly, you pretty much have only this option. You have to have one continuous data structure, and that's whatever the native array syntax is in the language. So we have a shared array. In this case, Leaf guarantees this is contiguous. This maps directly to a contiguous set of memory in memory, and there's no questions about that. And that's how we get the amortized time of theta 1 for get. And for each, this should be a bit more obvious, but we have the same thing. We have a theta of n. And again, theta of n, this, for most collections when you iterate, you probably want theta of n for iteration, but it's not true. Some collections can iterate much slower than this. Some collections have to reassemble keys and go through it and may have 2n or n squared. And again, because we have n here, we're not so much constrained though, because the linked list also has theta of n, because it just walks through elements. So we have no particular gain in time complexity for a vector for each over the linked list. And GetSize, of course, constant time as well. I'll just write that for completeness because we're talking about these things. Okay. Now one thing about the vector itself, let's go back. And space complexity, I introduced this last time. If you're not familiar with this, how much space does this take? And sometimes, again, this sounds silly, but this one's n. If we have n elements in the vector, it takes up n space in memory, plus little bits that we don't care about, like capacity and size. Again, this is not true of all collections. It may seem counterintuitive, but there are collections where the space is not the same size. Usually the space goes up because you duplicate the amount. Sometimes trees may have more, sometimes hash more. There are a few things like radix trees where it can actually be less than n, but that's really a special case, and you really have to, and it's really only an amortized amount, again, over lots of data to be amortized n. But for most collections, the most obvious one, you can assume that the space complexity is n. For every element in the collection, there will be at least, they'll take up that much memory. Okay, now we have this adding. We have the ForEach function, and what else could we possibly do with the ForEach function? Last time with the linked list, we made a sum function. Now the sum was very generic, and I'm actually going to copy that sum function Did I put it in main? Okay, I had a dump function, a dump reverse function. Let's copy them over. Because we said we gave the same interface, and instead of sharing these, I'm just going to do it the horrible way of copying and paste. These were all made for linked list, but all we did in linked list was create this ForEach function. So what that means is that we can call all the same things. Let's get rid of all these prints on this new function as well. So we can say dump q, we can do dump reverse q, and we can do sum of q, assuming it works. Let's see what the output of that is first before I explain them. And lax field. Uh-oh. Okay, we were doing a different value type last time. I was storing a container. So let's just do n. So it's a minor change. Sorry about that. I could make them be the same, but for each reverse. Okay. Oh, we don't have a reverse yet. So let's remove that one, and I'll show it again. Cannot ignore value 90. Alright, standard.println line. This returns a sum. Okay. Now, let me explain. We have a sum of 950 and we printed it out. So this is the output of the dump, and this is the dump here. And what was, it didn't quite work, but the idea was that when I looked at this linked list, we go back to that one, the linked list one, and I'll have small font size. It has essentially the same dump function, but it has an n.value instead. Now I think this is actually a mistake in the linked list code that it required n.value. It should have just required n, but you can still see the structure is the same. Now this is important for when making collections, and C++ holds this very strictly, and most other languages do as well. C# has explicit interfaces for this. Is that when I have a collection, this ForEach is part of the contract of that collection. Any collection needs to have this ForEach to be a sequenceable collection. In C# we'd call this an IEnumerable. It has a defined enumeration. Not all collections have enumerations, but mostly they do. And the idea is this dump function would work on absolutely any of them. Doesn't matter what the collection is, this dump function will work. It'll print it out. Now the other one we had from linked list is dump reverse, and so we can do the same thing. For a linked list, we had a problem on reverse, but for this one, let's just quickly write the reverse one. It has the same signature, t. We take a function that takes that value and just returns nothing. And you do standard range of size -1 to This is an exclusive range, so this might seem weird to -1. Or I don't remember for sure. So we should be able to have a reversed list now. Lists up 58. What did I do wrong? Yeah, in. Just any keyword. Okay, so that reverses it. So we have the reversed list. Sum doesn't change. And this is something I have to work on in standard range, is that when you have an exclusive range, it's kind of weird to write the reversed ones because you start at -1 and then go to -1. You'd rather have like an inclusive range and say go down to 0. Or you'd like to have a reverse range, but that's not the concern right now. This has the same time complexity of theta n. And if you recall from the linked list, I can go look at that again, the original linked list had a reverse for each reverse, but it was very costly. We didn't actually do the space complexity, and this is why we created the double linked list, was to get it down to 1 as well. Now there's one more thing we have to do to make this a proper vector. Let's get rid of these ones. Rid of the range. Okay. We want to write a remove function. So let's remove the element at 5, the one at index 5. Let's just remove that one. We don't have remove yet, but let's put it there. Find remove. Now remove is always kind of interesting for vectors. And what we need to do is we need to say for I in standard range, we have to start at the removed item. Sorry, this needs an index. This is an integer. We're going to start at the index and go to size, and we're going to copy it over. data-I equals data-I plus 1. Now this shifts them all down and effectively removes the item at size, but we have to remember to decrement the size as well. I don't think we need that. So I remove the element 5. Let's see if that works. Oh, I'm very good at making small mistakes. Sorry about that. Totally got this wrong. I plus 1. Okay. Now we go 50, 60, 70, 80, 90, and 100 is missing. So the fifth element, computer fifth element, because we start at the 0th element, index 0. So we removed it. We removed the 1 from the array. And that was a relatively simple operation. We removed that. And so 100 is missing, and the sum went down. And we can do the same thing again here. Let's just, instead of doing it here, let's show the differences here. Remove 5, and then show them all again. And we'll put a line in between, standard or print line. Okay. As you can see, it's 1 less, and we removed 100, so the sum is 1 less as well, which is what we'd expect. I'll leave those two do's there, but they're not important. Now, what is the time complexity of remove? It's one of those ones that's a bit costly. It's order n. And the reason why it's theta n is because we have to copy all this data over. Now, theta n, this is this is a really expensive theta n2, and this is one of the things that you often miss when doing complexity if you simplify it too much, is that this expand and remove function are very costly. But this ForEach function, which is also theta n, is not nearly as costly as remove, because ForEach is simply iterating. It's not copying any memory. And remove is actually copying memory. And this is one of the things you can do in complexity theory, is that you usually take the item of interest, what's most interesting, what's most costly, and you measure the complexity based on that. So for iteration, you're just saying, well, how many comparisons or how many steps do I have? And for adding and removing, you're saying, well, how many costly memory operations do I have? In this case, it's costly memory operations is n. But this is where it becomes really curious. If I actually measure ForEach in exactly the same way, I say, well, how many costly memory operations does ForEach have? It's actually 0. So constant of 1. We don't do constants of 0 usually, but so it depends how you measure. You could actually say ForEach in terms of memory allocations is none. There's no memory operations in ForEach. It doesn't even take the copy of them. It just passes them along. Whereas remove actually copies all the data. These were large objects that could be an issue. But we're going to stick with convention, and convention usually says, okay, for something like remove, well, how many operations do we actually have? And because if we compare this to a linked list, curiously, the linked list also had theta of n. But again, that's not the fair story, because in the linked list, it was actually iterations. The linked list only had one actual memory operation when it removed the item from the array and just patched up the links, so just put one, linked it to the other. Whereas this vector remove actually has to copy all of them. And so this is where you have to be very careful with complexity theory, is that although a linked list remove is theta of n and a vector remove is theta of n, the linked list could be faster. I say could because, yeah, there's a whole bunch of details involved exactly about how the memories line up on the CPU and how the iteration works. But let's just for a moment leave it at you have to pay attention to specifically what that is. So now we have removed and pushed, and we have adding, removed. And I had an add, and that's fine. So let's do another operation. Let's do some common vector operations. Let's make a pop operation. And we're going to make it a little bit more than just pop. We're going to say define pop back. It takes no parameters, and the return will be implicit. And we'll assume there's data in here at first. So I'm going to say var q equals, what is the last one? I'm going to say data size minus 1. Then we're going to remove 1. Then we're going to return q. And then we can do a loop down here. While q dot GetSize is greater than 0, we'll print it out. Standard.println pop q.pop. And pop means return, take one off the end of the list, reduce the size of the list one, and return that. And okay, 47. What did I do wrong? Remove. Sorry, I have to remove size minus 1. Unknown field, pop, yeah, okay, because it's pop back. Pop back. Add, sorry, what do I have here? Sorry, I used plus, that's bad. You can't add strings. Addition and leaf is strictly numeric addition. I don't like overloading for strings. Now, don't think I'm being totally ridiculous there, because although this won't be allowed plus def, because plus is strictly numeric addition, there is set concatenation, which is plus plus, and that'll combine two sets together. But for printing, you still can't do it because they're undefined types, and I don't have a library that's auto-converting quickly enough. But we can get back to that in a much later episode, string concatenation. So, I added pop back, we saved it, did we fix it? Okay, so it pops them all off. And pop back means it pops from the back of the list. And vectors are first add become first in the list, and then we add to the end of the list. And hello to our new viewers, whoever you are, say hi if you're there. And so we could also have a pop front. Let's say define pop front. Both of these are totally valid. Q equals data 0, remove 0, return Q. Now I can't just create a second array here. I'm going to have to do it this way. I can't just put a second while loop, because our item is actually empty after that. So pop front, it takes some values from the front. Now, let's do the complexity here again. This is where it becomes interesting. We have pop front and pop back are essentially the same. They both grab the data index, and we know this is theta of 1. We know getting a value is theta of 1. This is the same in both cases. Now removing, we said, is theta of n. Wonderful. Theta of n. That's not so good to pop an item off. And return is nothing. But there's a bit of a little trick here. If you really want to look at this very carefully, you can actually say that pop back is a time complexity of theta of 1. Now how does this work? Is that this data here is actually complexity of 1. But this remove size minus 1 is not order n. Because if you think about this for a minute, we're going to go to remove, and this range operation here is never going to do anything. This loop is effectively commented out because the index is always the last one in the list. So it's effectively just doing size minus 1. And this is one of the optimizations you can actually make in code. You can actually, well, let's just make the optimization, size minus equals 1. And this is actually the exact same code, just optimized. And this is why this is theta of 1. And let's put it back to pop back to show this is still working. Okay, and it still works the same way. We pop back even though we have this optimized version of the code. And what's really curious from complexity here is that I don't actually have to make that optimization to say this is order of 1, except if I say it without it. If I leave this in here, now I have a bunch of justification to make and say it, but really only theta of 1 when index equals size minus 1. Just some observations. This gets really difficult, but since we know we can do that, it's actually much better when doing a data structure to make an optimized form, because then you can guarantee it. You don't care what remove does. You can say, look, I guaranteed this. There are reasons where you may not want to just do this directly if there's some more operations to remove. But for now, we can simply say remove size minus 1. And we cannot do the same for pop front, because pop front has to do all the copying. So pop front does have order n. And you'll notice in some libraries, I think the original C++ one, it had this, it wouldn't define things like pop front. It would only do the cheap ones. So it wouldn't let you do something expensive. But something like edA-qa, it would allow pop front and pop back because they're both cheap. But on a vector, popping from the front is not a cheap operation. It's a rather expensive operation, depending on the size of the list. Now, I'm trying to think of what other function we could do in vector. What else is interesting? We've covered all the basics. Again, we have a vector, we have at times. So I made a mistake in error handling, but all of these things should have error handling on them as well. So if you had something like size equals 0, then fail with a string tag, no more items. But again, I made a small mistake here, and it's a really small mistake, unfortunately. So I can't do the handling, but so this is what it would look like. If the size was 0, you'd fail, saying there's no more items. And you do the same thing in pop front. I'll put 2 Ds on these. And the same thing would do with ForEach doesn't need them, but remove would have the same thing. Remove would have the same error handling. Remove is actually a bit more strict if you have indexes less than 0 or the index is greater than or equal to the size, then fail with a string tag. Remove from empty. But this doesn't work right now, unfortunately. Very sorry about that. I'll fix it for next time, and I can quickly look over it. But this shows the syntax. The syntax is really compact for this. I mean, this is the fail handling, error handling. There's also something that you actually have to write out the errors, but we don't have to worry about that. Now I'm trying to think of what else we can do with a vector. What other interesting things we can do. We can make a fold function. Folding is another interesting operation in high-level languages. So we're going to say fold, and this will be a typical fold, right? But let's call it fold for now. And fold takes a function. Fold is very much like ForEach. It takes a function that takes 2 values. It takes, yeah, this is where we can get really weird. You can just say a comma b, and it returns c. This may or may not work. I have to worry about this. So how do we fold? Now, when I say fold, and this returns a value as well, when you say fold on a list, so if you say list dot, so q dot fold, and you want to fold a star, for example, this would be equivalent to if q was a list of, say, 1, 2, 3, 4, 5. Folding it becomes q equals 1 times 2 times 3 times 4 times 5. That will be a fold operation. We imply in between all of them, we say what happens in between each of them. Now this we play with the parametrics a lot. This might not work perfectly, and so we have to take the list as well. Okay, I know what I'm going to have to do here. Okay, this function here is going to get really complicated, and so let's stick the fold operation directly on the vector itself. And then we can just say an op, because it becomes much clearer here what it is. Op takes a type of t and another type of t and returns a t. So whatever you do with the fold, it returns 2 t's. And we're going to be cheap a little bit first. We're going to say the first t bar, the first value is, multiplication won't work very well. So let's just assume I have enough data. So if we say size is less than 2, then return whatever the default value is. Actually, let's write the version first that assumes it's the correct size. And so our accumulating value equals op of data 0, data 1. And then we do the for each, but we'll just do it this way for I in standard range. And we're starting at 2, and we're going to size. We say accum equals the same operator. This is the actual folding part where you pass the previous value and you pass it the new value. And then you return the accumulated value. And if we did this right, we should be able to say standard print line fold sum is q.fold, and we're going to give an operation a comma b return a plus b. Now let's see if this works out. I probably won't get this the first time, but let's see if it goes. Duck parsing nothing, so I did the same probably thing again. Yeah, it's right here. That closes that and that. Q not found. It's way up here. Okay. So second, I'll show you this right at the top. The fold sum is the same thing. We have a sum and a fold sum. Now these work very differently. The sum explicitly did a plus on each item. It said plus, 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 and it had to do this lossy for various reasons, because it was the wrong size, because we were working with doubles in the other example. This fold sum now, it uses the generic fold method. Now to understand how useful that is, we're going to say, well, let's say fold product. This product's going to be probably way too large, which is an issue. It may actually be too large for integers. Okay, and so yeah, we've overflown the integers. So let's put I back down to 0 so we don't multiply by 10. Okay, and so now we have the product up here as well. For integers, product is not so useful. You may want to actually use floats. Floats has a better range. And you can do whatever else you want with the folding here. If we had more strings, we could actually fold strings. But I just want to show this quickly. I think this is the last thing I'm going to show. We have the product, and so sum could be rewritten. But this is where this sum, why it explicitly uses float, because it says even if you have integers, the float range is going to be good enough. And fold, you might be able to do the same way. But this is a basic fold operation. Okay, I'm going to just do one review of the stuff we covered on this, and then I'll call it a day. So what we wanted to do is we wanted to create a vector type in Leaf and go over the operations and complexity of it. A vector type is a specific type of container that keeps a list of items, and you can have random access. And our random access is this GetSize function. GetSize, or not GetSize, sorry, get. At any index in the vector, you can get the item right away, and it should be a strict constant of theta 1. This is always a constant time operation, and this is usually the defining quality of a vector. Most other collections don't have this property, and a vector is one that really does have that. Some of them go to the point saying that it actually has to be contiguous, which isn't so necessary. Hi, Aphelion, and welcome to the show. So this this strict requirement of having theta of 1, there's really no way to implement this without doing a continuous memory. This was an issue in C++ originally, that the vector, it never guaranteed it was contiguous, but I think they modified the standard to say it was. But there really was no other option. I mean, it's contiguous. There's just no way to provide that theta of 1 operation. Now, if we look at the next one we had to do was, the way this vector works is that we have an add function, and we wanted this what's called constant amortized time of theta 1, meaning that over time, not necessarily averaged out, but over time this works out to be an average of 1, but it's actually guaranteed. It's not really just average, it means something slightly different. And we did that by every time we had to expand the capacity of it, we would double the capacity. So we'd say capacity down 2, and then we copied it over. And so even though the expand was theta of n, the add function, due to the doubling in size, would be theta of 1. And this is what I specifically meant where I put in the chat the link for the more details, because if this 1 was anything less than 1, like 1.5 or anything, it's no longer amortized time of 1. That becomes linear then. It becomes theta of n. It has to be 2 or greater to become theta of 1. And so this makes sure our add is constant, is effectively constant time. Then we made a remove function. The remove function is a theta of 1 complexity because of the fact when it removes something it has to copy all the data over, and there's no way around that for a vector. This is the cost of this remove is because of the cost of get. And then we had a pop back function, and because it's an optimized function, because we always had the one item, we showed how remove doesn't actually have a theta of 1 and theta of n, but since we know that, we optimize directly so we can drop the size off. There's no copying involved here whatsoever. Now if I'm making a proper high-level class, there's a bit more I have to do in remove. I'm using fundamentals, so this item is still stuck in the data that we've removed. It's not actually been cleaned up. But since I'm using fundamentals, that's not an issue. If I were actually, once I put this in the standard library for leaf of vector, I actually have to make sure I do a cleanup here. And so this would be something along the lines of like q equals, or no, data size minus 1. And we're just going to assign it the default for the type. So type t. This will create a default item, and that'll clear it out. This should actually work. At least it won't break, but you can't see it. This is for if you had a shared pointer, this would clear out the shared pointer. If you had an optional, this would clear out the optional. We're just resetting it all the time. And I can leave this here, it's not a harm, but it's very important we do that in a full set, because otherwise you haven't cleaned it out. And this is the danger of not calling remove, because remove actually has to do this as well. Remove has to take the size minus 1 and clear it out. And so now you can start seeing the duplication here with this, that we have to do the exact same thing in 2 places. So this is the one case where I say, well, look, I know it's optimized, but let's actually just call remove instead, because I don't want to have to duplicate this code. But either way it works in optimization. And pop front, we showed that pop front, it calls remove. It has to be theta of 1, or theta of n, sorry, because there's no optimized form of this. You can't remove from the front of the vector because all the memory behind it has to be shifted over. GetSize is no problem to report. Get is also a very simple complexity. And ForEach is a time complexity of 1, or n. It just iterates over each item and calls your callback function. Obviously, I can't include the cost of the callback function. If your callback function is doing something that's really complex, in terms of complexity, like it's an n or n squared, it doesn't matter. All I can say is that ForEach is theta of n times whatever the function is. So this is really times the theta of, whoops. Actually, I don't even know how to note this. Times the theta of f. I think that's the correct way of noting it. So whatever the theta, whatever the complexity of f is, it's multiplied by n, and that's the complexity of ForEach. And it'll be same for reverse. And fold is just ForEach, so it's the same thing, theta n, and fold actually accumulates the data. And when you have a vector, since we're using integers, there's really not much you can do with it other than fold integers. But let's do another one here that does a float vector. Vector of float. And we'll add some values, and we can go back and add those times 10 values. The ones that overflowed before with integer. We'll say add 10s, and now we can show the product of this fold product. This is supposed to be F. And this shouldn't overflow. Okay. This is where the lossy was. How to say, yeah, lossy. I'll explain in a second why that has to be lossy. Okay. Now we have fold product of 3.6 times 10 to the 19th. Really large number. The floating point had no trouble handling this. Even if I made these times 100, I think that'll still be within the range of floating point. Doesn't make a big difference. Floating point in Leaf by default is it's usually double. Most platforms 64 points, because by default you virtually never want to use 32-point float unless you have a very specific reason to do so. Use the larger float, and that's why it's a default in Leaf. Now, why is this lossy I? Well, this is an interesting case, is that an integer by default is 64 bits. This is the natural integer size on platforms. Now, I also said a float is 64 bits. What does this mean then, though? This means you can't store the full range of integers in a float. So the operation, if you had var type I equals 0, integer equals 0, and var type f float equals ti, this is an error. The reason this is an error is because it means there's values you can store in ti that tf can't represent. And these are the really high end, because of the 64 bits in a float, a lot of this are the exponents. And so you simply cannot store all the integers in it. And Leaf is very strict in this regards. It will not let you lose data ever by default, and so it rejects it. And this add here, because add takes a float and I is an integer, this is why we put lossy on it. I'm explicitly saying, look, you can lose data here. I'm okay with this. I know what I'm doing. You can lose data here and convert this to a floating point value. And so that's why lossy is applied there. Okay, and that should be all we need. I think that goes over everything. I have a few to-dos here. The one to-do is I want to get the operator overload working so that these collections can have the natural subscript. The other to-do is obviously the error handling, which is a simple minor mistake. I know what it is, and I'll fix that quickly. And I don't know what other to-dos I had. I don't know. That's about it. So that's all I have for my show, and unless there's any questions, I'm going to sign off, and I'll commit this to Git and upload it if you want to look at this, at the code. I don't have the package for Leaf quite done yet, but if you're interested in running Leaf, just give me a shout and I can produce the package for your platform, either Linux or Mac. I don't have Windows running yet. And you can then actually play with these examples and test them out and work on your own. The next up on my list, other than these to-dos, is probably getting the error handling working. In terms of the compiler emitting messages that aren't totally retarded, because as you saw, our errors right now, these are not friendly errors. It's just I'm so used to them, and I wrote the compiler, I know what they do. So that should be I'll fix that. It's quite complicated to do. It's a lot of work, but I guess I have to do it soon if I want to show errors, because I'm actually forgetting some of them as well. Okay, and that's it. That's for a vector. If you do have questions watching this not live, just feel free to send them to me on Twitter. edA-qa is that handle at Twitter, or you can go to the Google Groups page or leaflang.org and look at the contact there. And feel free to friend me on Facebook if you want. We can change that way. Otherwise, please subscribe to my channel so you can see it next time. I will be doing more probably tomorrow I'll be doing some Fuse work. I'm doing the Dark Souls dice rolling again, and we'll finish off that app. Hopefully I can get a bit more done, and then hopefully I can start doing the Leaf broadcasts once a week. I'll try for Friday, sometime Sunday night. And I thank you very much for watching, and until next time, thank you.